Before we move on to rotations, let's solve a few more examples on linear momentum. A homogeneous chain of length L and mass capital M is hanging such that the bottom link touches the table. After the chain is released, a portion of length y remains motionless on the table. That means a portion of length y has fallen down onto the table. Every link stops at the moment it hits the table. Find the force exerted by the table on the chain at this point. Assume all links move independently. Okay, so when this chain falls a distance y onto the table will exert a force due to the fact that there is the weight of the portion that is sitting on the table. So it will be a reaction force on the weight, and also there will be a force of collision. So let's first start by noting that the table exerts a force which has two contributions: the normal force, which is reaction to the gravitational force, and then there is the force of collision, which will be present only during the collision. Now, this is a homogeneous chain of length L, which means that it has a mass per unit length, capital M divided by L, as its linear mass density. So if we ask what is the mass sitting on the table, it will be the mass on the table sitting on the table will be lambda times the length of the chain sitting on the table, which is capital M over L times y. Therefore, we can see that the weight that will be sitting on the table is lambda y g, which is going to be the normal force exerted by the table on the chain sitting on it. Now, when a link of this chain falls onto the table, it's going to have a velocity at the point it's going to hit the table, and then as soon as the link reaches the table, it stops. Okay, so there's a loss of kinetic energy. So at this point, when we have a portion of the chain that has a length y sitting on the table, the link hitting the table has a velocity that is given by the conservation of mechanical energy, because we're neglecting air friction here. The change in the kinetic energy plus the change in the potential energy is zero, because we have no non-conservative forces, no friction. So the link reaches the table with a velocity v, so 1/2 mv squared is its initial is its final kinetic energy, minus 0. It was released, therefore it initially had 0 velocity, and it's going to have a final kinetic energy. So we have a final kinetic energy mg L minus y, initial kinetic energy mg L. So this must be equal to 0. Therefore, we see that this link will hit the table with square root 2gy. Okay, so we have fallen a distance y, so we basically have a final potential energy mgl minus y, and we have an initial potential energy mgl. So the final velocity is square root 2gy when it has fallen down a distance y to reach the table. Okay, now during the collision time, delta t, the length of the chain hitting the table will be given by delta x, which is v times delta t. Now, if you notice, I actually considered this link, which has fallen a distance y, to calculate the change in potential energy, but it's going to be the same change in potential energy for all links, right? So because they're all falling a distance y to hit the table, the last link that is hitting the table also has a change in its potential energy of mgy, so which is basically accounted for by the change in its kinetic energy, 1/2 mv squared. So the length of the chain hitting the table in the collision time, delta t, is v delta t, which is square root 2gy times delta t, and it has a mass lambda times delta x, which is lambda times square root 2gy delta t. Now, during the collision, we have the impulse momentum theorem. Impulse is equal to the change in the linear momentum. So this is our impulse momentum theorem, which basically tells us that the force of collision, F collision, applied over the time interval delta t is equal to the change in the linear momentum m times delta v. Now, lambda times square root 2gy delta t is our mass, delta m is basically our mass hitting the table, and delta v is square root 2gy. So this is the mass hitting the table times delta v, which is the change in its velocity. So the final velocity is 0. The link that hits the table stops at that point. Initial velocity is square root 2gy because it has fallen down a distance mgy to gain its kinetic energy. Square root velocity, initial velocity square root 2gy before hitting the table. So you can see that these delta t's will cancel, and the force of collision is 2 lambda gy. So we can add these two contributions. The total force exerted by the table will be the normal force that balances the gravitational force and the collision. So this will be lambda gy plus 2 lambda gy, which is 3 lambda gy. Now, what was lambda? It was 3 capital M over L, homogeneous chain. Gy, g is our gravitational acceleration. This will be the force exerted by the table at this point in time. So to summarize, we have a homogeneous chain length L. The chain has fallen a distance y, so there is a length y sitting on the table. and it has a, this is a homogeneous chain, mass per unit length is a constant, capital M over L, and so lambda times G times Y is the gravitational force, the weight, and the normal force is equal in magnitude, so it's going to be lambda Gy, opposite in direction. And at this point, the link hitting the table has a velocity because it has a change in its potential energy of mgy. It's going to reach a velocity given by the change in its kinetic energy, 1/2 mv square minus 0, because it was released. So it hits the table with a velocity magnitude square root 2gy. And in the collision time, that means the length of the chain hitting the table is v delta t square root 2gy delta t, which has mass lambda times delta x. So the change in the momentum, linear momentum, is equal to the impulse that the table exerts. So we're going to have collision force times delta t, the impulse, if it's a constant collision force in the time interval delta t, that's our assumption, is the mass hitting the table times the change in its velocity. So the final velocity is 0. It stops as soon as it hits the table. Initial is square root 2gy. So we find that the collision force is 2 lambda gy, so that the total force is 3 lambda gy, adding the contribution from the normal force, which is counterbalancing the weight. So we have 3m over L gy as our final answer. Okay, so let's move on to the next example. So we have three masses here. Particle A, which has mass m, particle B, which has mass 4m, m and 4m are connected by an elastic coil which is initially relaxed, and particle C has mass m. It's approaching the system of A and B with a velocity v0 on a horizontal surface which has no friction. So block C with initial velocity v0 I hat hits A and stops, and there is no friction. Find the maximum compression on the light spring. We neglect the mass of the spring. Spring constant K if A and B are initially at rest and the spring is initially relaxed. Okay. So for this system of A, B, and C, the net external force acting on the system is 0. So we're going to have no change in the linear momentum in the x component because we don't have any forces on the x-axis. The initial momentum, linear momentum, is m v0 I hat, which is the momentum of C. The other ones are at rest. The final momentum will be, because C will hit and stop, m plus 4m times v final. So initial linear momentum is equal to the final linear momentum. We must have mv0 is equal to 5m v final. So that implies the final velocity will be v0 divided by 5 for the system of m plus 4m, which is A plus B. Now, since I have no friction in the system, the kinetic friction force is 0, there is no change in the mechanical energy of the system. Delta E mechanical is 0. So delta K plus delta U should be equal to 0. The final kinetic energy is 1 over 2. I have a total mass 5m with the final velocity Vf square. The other one, mass particle C, has no final kinetic energy. Initial kinetic energy is 1/2 m V0 square. The initial potential energy is 0 because the spring was relaxed. Final potential energy will be 1/2 kx squared, the potential energy stored in the spring. So the change in kinetic energy, K final minus K initial, is 1 over 2 5m. The final velocity was V0 over 5, V0 square over 25, minus the initial kinetic energy 1/2 mv0 square. So this gives us, this 5 will get rid of this 25 and make it 5. 1 over 10 minus 1 over 2 mv0 square. So we have a net change 2 minus 10 minus 8 over 10, which is, so 2 minus 10 will be, or we can say that this is going to be 5 over 10. So 1 over 10 minus 5 over 10 minus 4 over 10, which is minus 2 over 5 mv0 square in the change for the change in kinetic energy, which is minus the change in potential energy, U initial minus U final, which is minus 1 over 2 kx squared. Okay, so we can basically calculate x from this equation. 4 over 5 mv0 squared is equal to kx squared. Therefore, x, the maximum compression in the spring, is v0 square root 4m over 5k. Okay, so to summarize, we have a frictionless horizontal surface. A and B with masses m and 4m are connected by an elastic spring which has spring constant K, negligible mass, and initially relaxed. No potential energy stored. A and B are initially at rest, no kinetic energy. C has a kinetic energy 1/2 mv0 square. It's approaching the system of m plus 4m with an initial velocity v0 I hat. The net external force on the x-axis is 0 for the system of A, B, and C. Linear momentum is conserved on the x-axis, so we write the initial linear momentum equals final linear momentum to find the final velocities of m and 4m to be v0 over 5, and the change in the kinetic energy of the system will be stored as potential energy on the spring, and we can calculate the potential energy, the compression in the spring when we have reached this final velocity of A and B, and delta K is equal to minus delta U gives us the compression in the spring to be V0 square root 4m over 5k. Now, as a final example, two blocks A and B with masses m and m over 2 are initially moving together with a velocity v0 I hat and are connected by a light spring initially relaxed, spring constant K. A block of mass m over 2 falls through a height h and sticks to B. So this falls and sticks to B. Find the maximum compression on the spring. Okay, so when I look at this system and I look at the net external force on the x-axis, this is equal to 0. Therefore, I have conservation of linear momentum on the x-axis. So we have an initial linear momentum mv0 plus mv0 over 2, and C does not have any velocity on the x-axis, so it happens to fall directly onto B and sticks to it. So basically B was passing under C when it hits the it's B, so it's going to be only y component of velocity of C. So this will be equal to the total mass now 2m, m plus m over 2 plus m over 2, v final. So the final velocity will be 3v0 over 4. Okay, so the initial kinetic energy I have here is 1/2 m v0 square plus 1/2 m over 2 v0 square. So this basically makes 3m over 4 v0 square. The final kinetic energy will be 1/2 2m 9v0 square over 16. So this is going to give me 9m v0 square over 16 final kinetic energy. So the change in the kinetic energy of A and B is K final minus K initial, which is 9m v0 square divided by 16 minus 12m v0 square divided by 16. So 3 over 4 makes 12 over 16. So this is minus 3 mv0 square divided by 16. And that must be equal to minus the change in potential energy. Why? Because I have no friction on this system. And therefore, the potential energy stored, 1/2 kx squared, will be equal to the decrease in kinetic energy, which is 3m v0 squared divided by 16. So this will give us, for the maximum compression on the spring, v0 times square root 3m divided by 8k. Okay, so I want to make a few points here. Now the fact that C is falling on B, basically it's going to have only a vertical component of its velocity. It's going to apply a collision force on B, and there will be a reaction force from B onto C, etc. But everything is happening on the y-axis. So here, for the system of A and B, I have no external force on the x-axis and I have no friction, so I must be able to write conservation of linear momentum on the x-axis. And in terms of the energy of the system of A plus B, I have the initial kinetic energy 3m over 4 v0 square, and there is going to be a change in the kinetic energy of A and B because of the collision between C and B. I'm going to have a final kinetic energy that will be influenced by conservation of linear momentum here, because there will be a final velocity, common final velocity Vf for the system of A and B. So this change in the kinetic energy of A and B, or A plus B plus C at the end, because C sticks to B, is going to be equal to minus the change in the potential energy, because I have no friction in the system. Mechanical energy is conserved, so I must have basically a final compression on the spring, which will account for the decrease in the kinetic energy of the system, so that the compression will be v0 square root 3m over 8k finally.